All right, so this critical density is, which comes from the modern value of the Hubble constant, and in Einstein's equations. It turns out to be about 9 times 10 to the minus 27th kilograms per cubic meter, and that amount is roughly about 5 hydrogen atoms per cubic meter. All right, so that's essentially how much matter is necessary to collapse the universe back in on itself. That's called the critical density. All right, so now we're going to look and see, what can we find out from these different surveys of the universe. All right, so and probably the best one we have is the Sloan survey. Just to let you know, if space is homogeneous, there are 3 possible outcomes for its structure. It's either closed. That is, the universe will collapse back on itself. It's flat. It's exactly the critical density turns out to be exactly what the universe is, and it's still a flat universe. The geometry, we're talking about the geometry here, and then of course there's an open universe, which where there's not enough mass for the critical density to collapse the universe, and so it continues to expand forever. All right, so then there are 3 possibilities that can be described with by comparing the actual density to the critical density, and so the actual density is omega, and the critical density is omega naught. All right, and so generally what we do is we say it's actually we look at the ratio of omega to omega naught to omega. Anyhow, if the actual density is less than the critical density, of course that's not enough. That's not enough to collapse the universe. If it's exactly equal, then it's a flat universe. And then if it is greater, if the actual density is greater than omega naught, the critical density, then it's a closed geometry. And there's consequences to these that have to do with the shape of space itself. So, for example, if you think about the surface of the Earth, it's a closed system in and of itself, right? So, the basic idea of a closed system would be if you travel anywhere, you got to stay in a straight line. So, just imagine the surface of the Earth. Don't worry about the mountains and the ocean and stuff like that. Just assume that you can, just travel in a straight line all the way around the Earth. And so that's the point, is you would go all the way around the Earth and then come back. So this is behind the Earth, and then you'd come back to your starting point, right? That's the idea of a closed geometry, right? So for a closed universe, that's exactly what would take place. I mean, it might take billions and billions of years for space travelers to be able to do that. I mean, we really don't know, but that's what a closed universe would mean. All right, and so remember, the closed universe, the actual density is greater than the critical density. All right, for an open universe, then the universe would be more shaped like a saddle, and it turns out, like, if you were to look at it actually has a lot to do with like parallel lines. If the universe was this shape, the shape like a saddle, you couldn't have two parallel lines would diverge. They would go away from each other. With a closed universe, two parallel lines would intersect eventually. With a flat universe, that's the original universe that we call Euclidean geometry, right? Just nice straight lines. There's parallel lines that could go on forever, right? And never ever cross each other. All right, so So will the universe keep expanding, or will it collapse in on itself? So we have to look at the actual density, and so to do that, we do these gigantic surveys in particular directions, in any direction we can look. But you use this idea of the cosmological principle that it's homogeneous. Doesn't matter. If you look in large enough scales, the universe is basically the same. So, and also isotropic. And so when we do this, we find that we only come within just a few percentage of this critical density, right? And then people started saying, well, what about the dark matter? I mean, it seems to be most of the matter in the universe is this dark matter. Would that close the universe? And see, even that, you only get to about 0.3 times the critical density. So you're still far below the actual critical density required to close the universe. Right now, it's up to this point in this talk, we have it seems like there's, including the dark matter, or the best estimates we have about how much dark matter, there's just not enough to close the universe. The critical density is still greater than the actual density. And then back well, it was before the year 2000. There was this huge study by two separate astronomical groups, these large groups that consisted of astronomers from around the world, and one of the things that they did is they looked at type 1. They were actually type 1A supernova, just to let you know. So remember, just as a reminder, type 1 supernova, or type 1A, as they're better known, are always the same luminosity, or nearly so, right? So they're very, so no matter where they go off in the universe, whatever galaxy they occur in, you know exactly what their peak luminosity is. Right, and so you survey the all these different galaxies, and you look for a type 1 supernova to go off, and when it does, you use that information to figure out the distance to that galaxy. All right, so there was this systematic approach to try to figure this out, because people said, well, wait a second, maybe we're getting this wrong. Maybe the universe is already decelerating. Maybe we're just not seeing that. So let's look out into the universe as far out as we can, and we'll get as many of these supernova as we can, and try to figure out what the Hubble constant was, way back into, towards the beginning of the universe. And, was it, it was probably faster. The acceleration rate of the universe, the expansion of the universe, was faster back towards the beginning of the universe, right? 13.8 billion years ago. So that's what these two teams actually that went out and tried to do this, and they found something unbelievable. And I was one of the people that for first very much doubted the results of these experiments. I thought that there was something wrong, that there's no way that there could be this acceleration. So here's what these folks found, is that the universe is not accelerating at the same rate, and in fact, it's not slowing down its acceleration, it's actually speeding up. So as time goes on, the universe is actually expanding more rapidly. Now, it takes, of course, it takes billions of years to observe this. So we're looking at, galaxies billions and billions of light years away, and so but like I said, at first people doubted this, and then more, and of course in science, anytime someone comes or some group comes up with an idea, and it seems to challenge the notions that had been thought to be true for a long time, then lots of people start to investigate that, and then more and more people, more and more scientists around the world found that indeed this is exactly what's taking place, that the universe it's as though somehow there's some kind of force in the expansion of the universe that's causing it to go faster. So just here's a silly analogy, but if you're going onto the interstate with your car, you're going onto the on-ramp, and you turn, and you got a nice straightaway, and you put your foot on the gas. Of course, that's acceleration. That's positive acceleration, right? Deceleration is, of course, when you put your foot on the brakes and you slow down. But there's something that's causing this to take place, and nobody knew, and we still don't know what it is. Of course, just like dark matter, we gave it a name, and the name is, so the name of this repulsive force, this force. So here's a nice picture. The name anyhow is called dark energy. All right, and so what the dark energy is doing, so it's kind of like imagine a spring at different stages of the during the ages of the universe, and so the spring is pushing the universe apart at a certain rate, and then as time goes on, it's pushing with greater force, and so the universe expands in a it accelerates. It accelerates the expansion, and so that is what was discovered, and all the evidence shows that this is true. It's a very bizarre thing, but it's very odd. All right, let me tell you a little story here about Einstein and one of the greatest mistakes he had ever made. Or he actually considered it his greatest mistake, and for his time it really was. So Einstein comes up with the theory of general relativity right around 1915, 1916. I think 1916 he publishes it, and almost immediately he uses the equations of general relativity to see what's going on with the universe, right? He applied those equations to the universe at large. And at his time, you have to understand that he was a scientist of his time. Everyone at the early part of the 20th century thought that the universe was infinitely old, and that essentially, locally, some stars are going to be born, some stars will die, blah blah blah. But essentially, the universe was infinitely old and unchanging. So when Einstein solved the equations for general relativity, he expected what's called a static solution. That is, the universe is never going to change. It's always going to be the same. That's exactly what he didn't get when he solved those equations. He found that it was a dynamic universe, that the universe was changing. In fact, when he did this, it was like 10 years before Edwin Hubble made the discovery that the universe was expanding. He could have actually predicted what Hubble discovered experimentally roughly 10 years later in 1929. Anyhow, Einstein used this thing called the cosmological constant. It's a symbol. I think he used lambda, what this cosmological constant was sometimes we call that in science a fudge factor. It's completely bogus. It was something he threw into the equations to make the solutions come out static and not come out dynamic. And it certainly worked. But later in his life, 10 years later, when Hubble made this great discovery, Einstein said, "Hey, if I didn't throw in this cosmological constant, I would have been able to predict that." And Einstein was a wonderful scientist. He couldn't be right on everything. That's,